Okay. Good afternoon, everyone. Am I audible? Sorry. Okay. So today is the seventh interaction session on reliability-based structural design. Okay. So this course is basically instructed by Professor Onassis Chakraborty, IIT Guwahati. My name is Devashish Panda. I'm a research scholar and Prime Minister Research Fellow at IIT Guwahati, and I have been allotted to this course as PMRFTL. So every Sunday from 3 to 5 p.m. we meet for the interaction session and we discuss the current week topic. We solve different numerical problems using pen and paper and also using MATLAB. So today we will go through the second order reliability methods where first we will go through the Breitung's models. Then we will code the algorithm in MATLAB and we will solve different kind of problems using the Breitung approximation for solving the second order reliability problems. And also we will compare the second order results with the first order reliability method results, and we will see when the second order reliability method will give the better results. And then we move forward to the weight model where we just discuss the model. We will code this algorithm to solve the second order reliability problems, and we will solve similar kind of problems, and we will check or compare the results from Breitung model as well as the Tate model. So basically we will move around today the second order reliability method where we will code that Breitung and Tate model, and we will solve different kind of problems, and we will see that how the probability of failure will differ if we go for the first order reliability method and if we go for the second order reliability method. Okay, so let's start. So before going to the second order reliability method, just recall or just quickly revisit the concept of the first order reliability method. So during the few interaction session or last few interaction session, more precisely last few interaction session, uh, we solved different problems using first order reliability method. In first order reliability method, recall the probability of failure PF is calculated as nothing but standard normal variate of phi of minus beta, where this beta is nothing but the reliability index, and we solve first order reliability methods using the concept of kernels as well as Hasofer-Lin reliability index. And we saw that Hasofer-Lin reliability index address the mean value the lack of invariance problem which occurs in mean value first order second moment method, or precisely if we go for the Cornell's reliability index. So just just recapitulate that probability of failure from first order reliability method, we get that phi of minus beta. Okay, and beta we can calculate it uh, that gradient based form method we have already seen it. Now the thing is, consider that we have two limit states. Okay, one is nonlinear, this one, say for example this is g of x1 nonlinear limit state, and we have another limit state, this is g of x2, and this is perfectly linear. Now if we have these two limit states, for example if we have these two limit states, now as per the definition of beta, we will get the same beta if we solve using the first order reliability method. This point we will get uh, as per the Hasofer-Lin reliability index, beta is nothing but the shortest distance from the origin to the limit state function in standard normal space. So if we solve this limit state using first order reliability method or form, we will get same probability of failure, because the beta value for these two will be same. Say for example beta is 3 for these two cases, for example, let's say. So we will get pf for this gx1 phi of minus 3, as well as say pf2 for the nonlinear function we will get, or the linear function we will get the same value of probability of failure, whatever this comes. We can calculate it from the standard normal table, or we can calculate it using calculator or MATLAB. Now the question here is, in reality if you see here, the failure probability for these two limit state is different, or the failure probabilities of these two limit states are different. Like if you see, this reason for the nonlinear limit state is the failure reason or unsafe reason, but for the linear limit state, the entire this reason will be the failure reason. So obviously it is evident that the failure probability for these two limit state will not be same. But if we use the gradient based form method, we will have same probability of failure, because the beta value here for two cases will be same. Now why this is happening? So next the question will come that if we have highly nonlinear limit state, then obviously the form result, you cannot reliable on the form result, because it will give the result as per the linearization. Now why this phenomena is happening, we will just discuss. So in form, recall, in first order reliability method, we truncate the Taylor series expansion of the limit state function up to the first order term. Here we truncate the series. Here we haven't considered the second order term or the cross term here, right? Now, with respect to the basic mathematics, we know that the curvature, basically the curvature of any equation is related to the second order derivative of this nonlinear function with respect to the basic variables. It is clear. So if we want to incorporate the information about the curvature for the nonlinear limit state function, we need to go up to the second order term, and we need to find it out the ways how we can incorporate the information about the curvature in the form problem. So basically in second order reliability method, we go up to the second order term in the Taylor series expansion of the limit state function, right? That means eventually when we incorporate the second order derivative term in the calculation of the probability of failure, obviously the second order reliability method will give better result when there will be nonlinearities. So basic difference in first order and second order method: in first order method we consider up to the first order term. That means basically we linearize the limit state function by truncating the series up to the first order term, and in second order reliability method we go up to the second order term, so that the curvature related to that nonlinear limit state function we can incorporate within the estimation of the probability of failure. That is the basic concept for the second order reliability method. So obviously if you have the linear function or linear or nearly linear function, that means the nonlinearity, the degree of nonlinearity is less or low, we can go for the first order method. It will give the reliable results. But if there is nonlinearity present in the limit state function and the nonlinearity degree of nonlinearity is higher, then obviously we need to go for the second order reliability method. So let's see, in first order approximation we have seen that we truncate this series. This is the GZ. Already we have seen this formula. This is nothing but that Rakowitz-Fischler algorithm we already have solved in first order reliability method. So what we have did, we have done in the first order reliability method, we truncate the series up to the first order term. So this is we transform the limit state function into the normal space to standard normal space. Then we did the calculation when we find the beta is nothing but minus gradient of z star divided by Euclidean norm of gz star. Now z stars are nothing but the design points, and for the design points we have seen that according to Haushofer-Lind reliability index, these are the nothing but alpha times beta. Alphas are the direction cosines, we have already seen it. Now the thing is, if we rotate this z coordinate, that means the standard normal space, to another coordinate z star using some rotational matrix, or we can say we apply some orthogonal transformation to the z space and rotate this z space such that the last you know variables in z, that means the final design points which you have which we get from the first order reliability analysis, that should be coincide with the beta value. Or in a way, we can say we have the direction cosines here for the corresponding beta that will coincide with the beta value. Now, if we do that and apply the orthogonal transformation here, we can see that our gz will become zn prime plus beta, and we can say that zn prime equals to beta. That means the first order approximation will give you the beta value. That means if the function is linear or nearly linear, we can go with the first order approximation. Now, if we go for the second order approximation, here we consider the second order term in the Taylor series expansion, right? So gz in z star point, it's a reference point for this expansion, and we have this. Now, if we simplify this equation, like for c, we have denoted is the gradient of gz star divided by Euclidean norm of gz star, and d is equals to nothing but the double derivative of the gz star by Euclidean norm of the gz star. And if we simplify it, we will get this. Now, if we apply the orthogonal transformation, like for we want to rotate the z space into z prime space, where the last variable will coincide with the beta. Now, why we are doing this? We just want to incorporate the information about the curvature, or we can say the information about the curvature around the MPPs. That will actually improve the estimation of the beta. So we can have the second order approximation form in this term, that Zn equals to beta plus half Z transpose A Z prime. Now here that A matrix that actually contain the information about the curvatures, and A is nothing but it's a diagonal metric. And how we can form it? Like a transport dr. That means the rotational matrix or the transformation matrix is important for this estimation. Now, this is the second order approximation. If we go, or if we see that, okay, here there is a matrix that expect beta, we have some information here regarding the curvature of the limit state function around the MPP points. Now, how we can incorporate it, or how we can solve this to find out the final probability of failure? So there are some numerical methods are there. So here, asymptotic integrals are used. So actually, for this course, two models have been discussed, like Breitung as well as the Tvedt model. So Breitung actually go for the asymptotic integral. So if we directly go to the Breitung model, how he proposed to incorporate the information about the curvature. So let's see. So first, 1984, that Carl Whitung has proposed an closed form solution to calculate the second order reliability. That means considering the second order term. Now, how to incorporate mm, that information about the curvature? So he proposed some closed form relation based on the theory of asymptotic integral. Now I will show that asymptotic approximation. Actually, he published that paper. I will show that paper. So first, let's see the model first. Then we will go to the paper, uh, and and we will see the asymptotic approximation part. So he said that probability of failure, or more precisely, the probability of failure, the second order probability of failure, will be approximately equals to phi of minus beta. That is nothing but the probability of failure we are getting from the first order reliability method form, and then some correction over this beta. And here you can see that 1 plus beta into kappa. This kappa actually contains the information about the principal curvature around the MPP. Now our task is to find out this kappa value. So probability of failure in second order method, or PF SORM, we can have like phi of minus beta 1 plus beta into kappa j, and this is nothing but the multiplication sign whole to the power minus half. And once we have the probability of failure, we can calculate the beta. Beta will be nothing but phi inverse minus of phi inverse probability of, or second order probability. Now we will understand, let's understand these terms one by one and how we can get this. So here the beta value is calculated using the first order reliability method. So first we need to solve the problem and need to get the beta. we need to get the final alphas, and we need to get the final design points. These three things we need to first calculate. Now once we have these three things, we need to construct that R matrix. Now we will see the algorithm one by one. Okay, so here how we can get this model. So basically this is the Breitung model for second order reliability method. How we can calculate the probability of failure or the second order probability of failure? It's nothing but the first order probability of failure and some correction over it. Now we see that kappa are nothing but the principal curvature, or the information denotes the principal curvature of the limit state, right? So first we need to, what we need to rotate this z space into z prime space such that the last variable, so here we can see, here we have z1 and z2, two variables, the final variables. We have beta. So we rotate this space into z prime such that the last variable is z2. So z2 should be coincide with the beta, or in a way z2 should be coincide with the final direction cosines. Okay. Now once we did this transformation, we will get the values of kappa. Now, how we can get the kappa value? We will see in a minute in the algorithm. So here he have developed this closed form solution using the concept of uh, asymptotic approximation. Asymptotic approximation. Okay. Now for the asymptotic approximation, I will not go into the derivation and all these things of asymptotic approximation. You will see the asymptotic approximation here. This actually paper published by Carl Breitung himself in 1986, I think. Yes. So if you go through this paper, you can see the asymptotic integral, how he have used to formulate or to establish the relation between the Jacobian and the kappa. So if you want to go through this, or want to have more knowledge about this asymptotic integral, you can go through this paper. This paper actually written by or authored by Carl Breitung, that Breitung model we are discussing now. So we will not go into the asymptotic integral. We will stick to the Breitung model, how we can get the kappa value, how we can solve this problem using that model proposed by Breitung, and how we can get the probability of failure and beta. So he used that asymptotic integral to establish the relation between the Jacobian and the principal curvature around the minimum distant point. So if once we have this information, we can easily construct the equation whatever we have seen. So we are not interested to see how we have formulated this. Rather, we are interested how we can solve this problem, how we can get the kappa value, how we can get the probability of failure value, and how we can get the beta value, all these things. So let's see the algorithm first, how we can get it. So if we want to solve any problem using second order reliability method using Breitung approximation, first what we need to find it out? First we need to find out the final beta, final alpha, and final z value using the first order reliability method, either Rakowitz or Rakowitz-Fissler algorithm. We have already seen it. So first we need to solve the problem using first order reliability method, then the correction for the curvature will be incorporated within this equation using this form. So first what we need to do, we need to have the beta, final alpha, and final design points in our hand. Now once we have this information, that means we need to first run the first order reliability code, that means Rakowitz or Rakowitz-Fissler algorithm, to solve this, to find out the beta, alpha, and z, final beta and alpha and z. Now once we have these three values, we need to construct the R matrix, because recall that we transferred z space into some z prime space where the last variable should coincide with the beta vector or the final direction cosines. So this is more important, how we can get the R matrix, the rotational matrix, or the transformation matrix. So this matrix we can have, or we can get this matrix in two steps. In first step, we need to construct the R naught matrix. R naught Now, what are the properties of the R naught matrix? R naught matrix will contain the last row of the R naught matrix will be the final alphas. So, for example, if we have two variables x1 and x2, in Z domain we will have two variables z1 and z2. So, finally, we will have z1 prime and z2 prime, and corresponding to them alpha 1 and alpha 2. Now, once we have that alpha 1 and alpha 2, so in R naught matrix, the last row will contain the final direction cosines, because when we will rotate the space, the final design points should be coincide with that beta value or this alpha value. So obviously, the last row of this rotational matrix should be the or must be the values of the direction cosines, whichever we have get from the form analysis, and the diagonal term will be 1. Rest all are 0. Now, once we have that R naught matrix, we need the that Gram-Smith orthogonalization algorithm to calculate the other rows of the matrix. So how this Gram-Smith orthogonalization work? So here the row vectors are orthogonal to each other by Rn equals to R0n. That means the last row will be the same. Then from the n minus 1th row to first row, that means last row already we have from the R naught matrix. Now from n minus 1 to 1, we can calculate the rows using this formula. This is the actually Gram-Smith orthogonalization. We will solve problem. We will see how we will use that formulation to get the other rows, and we will code it too. Now, once so up to this step, we formulate the R matrix, or we get the values of the R matrix. Okay. Now, once we have the R matrix, we need to formulate the A matrix. Actually, in the A matrix, the information about the principal curvature are there. So how we can calculate the R matrix, or how we can construct the A matrix? R matrix, we have seen that how we can construct the R matrix. Now how we can calculate or construct the A matrix, we will see. So A matrix is such a matrix whose element like Aij. So this is A matrix. Say each element of this A matrix, so A11, A12, these elements will be nothing but R D R transpose by Euclidean norm of G Z star. Now what is D? D actually here the matrix which contain the second derivative of the performance function in the standard normal space. Second derivative. That means it actually incorporate the curvature within our estimation, or within our estimation of the probability of failure estimation. Okay. So once we have A, that means within that A already D sit here. That means the information about the principal curvature are already incorporated within here. Now what we will do? Remember, this was the final approximation for the second order reliability method. So if we drop the last row and last column, that means n minus 1 row and n minus 1 column of the A matrix, so the remaining formula will approximately equals to or get the shape of this equation. Now once we have this A matrix, after dropping that n minus 1 and n minus 1 element, the remaining A matrix will be used to find out the principal curvature or the kappa values. That means the remaining A matrix, if we do the eigen operation, the eigenvalues of the remaining A matrix will be the kappa values. So Ki11, K12, if we have the bigger matrix, we will have the larger numbers. Now once we have evaluated the kappa values, now we can directly, so you can calculate the probability of failure of second order probability of failure using the Breitung approximation, and that will be equals to phi of minus beta and multiplication of 1 plus kappa j beta to the power minus half. Beta already we calculated using first order reliability method. Kappa we found it out from the A matrix or the component of the A matrix, and once we have this probability of failure, we can calculate the beta. Beta, the reliability index, beta is nothing but phi inverse of PF sum. So this is the algorithm to solve reliability problem or the second order reliability problems using the Breitung approximation. So I will go through it once again, then we will solve some problem, then we will code the algorithm in MATLAB and solve different problems and verify whether this second order method using the Breitung approximation will give the better results or not. So let's go through these steps once again. So first, what we need to do, if we need to solve second order reliability method using Breitung approximation, first we need to have the final beta, final alphas, and final design points using the first order reliability method, because we have seen that Breitung approximation actually it corrects the first order reliability results and incorporate the information about the principal curvature and give us the second order probability of failure results. So first we need to have this information beta, alpha and all these things. That means we need to run the Requies or Requies-Fissler algorithm, or we need to solve the problem until we get the final value of beta using Requies or Requies-Fissler algorithm. Now once we have the final alpha, we can construct the R matrix. R is the actual rotational matrix. So R matrix is formed in two steps. First step, we need to form the R naught matrix. R naught matrix contains the direction cosines as the last row, because in the transformation we have seen that the transformation should be such that the last variable should coincide with the alphas or the betas. So obviously the last row should contain the final direction cosines, which or final direction cosine associated to the final beta. Now once we have R naught, now we apply the Gram-Schmidt orthogonalization to get the other rows from n minus 1 to 1 using this matrix operation. Now once we have the R matrix, that means the rotational matrix, we need to formulate the A matrix. A, actually this matrix contain the information about the principal curvature. And A, how we can get the component of A? So Aij, say for example Iij should nothing but it will be R D R transpose divided by Euclidean norm of G Z star. And norm of Gz star nothing but the gradient of the limit state function in the standard normal space. Okay, so when we have formulated the A matrix, say for example A, we have n cross n matrix, n cross n matrix we have. Now what we need to do, we need to drop the last row and last column of this matrix to get nearly approximation of this formula or the second order approximation formula. Now once we have this A without n minus 1 and n minus 1 column, now the remaining A matrix is used to calculate the principal curvature. That means the remaining A matrix, do the eigenanalysis, the eigenvalues will be the kappa values. Now once we have the kappa values, this is nothing but the Breitung model. Now use all the information in the Breitung model, you will find out the probability of failure. Once we have the probability of failure, we can calculate the beta value. Beta value will be nothing but phi inverse of probability of failure. So minus, obviously minus will be there. So phi inverse of that. Now we will see one problem step by step. Then we will go to MATLAB and solve this algorithm. So I hope this is clear how or what are the steps we can follow to have the probability of failure. Bob, have you get this? Got this.
Yes, yes, I'm following. Yes,
Okay.
thank you.
It's like in second order method, Breitung approximation is nothing but like the correction over the first order approximation, or to incorporate the information about the principal curvature we need to follow these steps to get the R matrix, and once we have the R matrix we get the kappa value. Once we get the kappa value we can directly have the probability of failure. Now let's solve one problem, then only these things
Okay.
will get more clear. Okay. So this is the problem. This problem is taken from Haldar Mahadevan book. If you go through that Haldar Mahadevan book, you will find out this problem. So this problem says, consider a cantilever beam which can carry a deterministic bending moment. That means your moment is not random. That means it has fixed value of mu and mu, only mu. It will consider that like only the mean value. That randomness will not follow here. So only we have two random variable fy and z. Okay, the deterministic value of moment is given. The sectional modulus z and the yield stress fy are statistically independent. Great. Calculate the reliability index considering Z and Fy as the normal and log normal variable. That means Z follows the normal distribution and Fy follows the log normal distribution for the plastic moment carrying capacity. That means your limit state function is given Gx is equals to Fyz minus M. That means you can simplify further to, that means x1 x2 minus M. M is the deterministic value, so we don't need to, M value is already given 1140, or directly write it down x1 x2 minus 1140. So first what you need to do, if we want to solve the probability of failure using Breitung approximation, first we need to solve up to the final beta and alpha using the Rakwitz's algorithm. So recall the Rakwitz's algorithm. What we need to do, first we need to convert this into standard normal space. Okay, Z space. How we can convert it? Like, say Z1 is equals to nothing but x1 minus mu x1 by sigma x1. We have already solved different kind of problems using this formula. So here we can see that we have one log normal variable for Fy. So here for Fy, these are the equivalent normalization. Like we have already seen how we can convert the log normal to equivalent normalization random variable. Then if we solve it, if we solve the problem, we will get these values. Beta is equals to minus 5.059 and final alpha 1 alpha 2 is minus 0.836 and 0.543. And these are the design points minus in Z domain, and these are the design points in X domain, right? Like Bob, you were asking like why we go for this reliability analysis, and in the practical example, like this problem, if we go with these values, it will not assure the probability of failure or some beta value. But if we do the analysis and take these two values, it will assure that it will give the beta value as this and corresponding probability of failure this, if the randomness of Z and Fy is considered. So that's how, if in one parameter of the limit state, if it is random, so you can check that if I consider the mean value, then what should be the probability of failure? If I want to get this probability of failure, what should be the design points? Vice versa. So to get the design points corresponding to some probability of failure and beta value, we incorporate first order, second order reliability methods or different kind of simulation based techniques to get that final point. If we design with respect to these points, we can see like Fy. Initially the Fy value was 38, but it says if you consider the Fy value is 24.59, you will have the probability of failure corresponding to beta is 5. That means you will have lesser probability of failure, right? And if we consider Z, this value, you will also have the lesser probability of failure. You don't need to go for these higher values. The higher values are provided here. So to make it economical as well as safe against the randomness, we can go with that. So first we need to do the first order reliability analysis using Rakwitz's algorithm. We did it and we get these values. So these are the like prerequisite for the SORM problem or the Breitung model. Now, once we have these values, we need to first form the R matrix. Now, recall how we can formulate the R matrix. R matrix, first we need to calculate the R naught matrix. So, R naught matrix will contain the last row as the design point, the direction cosine. So, here the final direction cosines are minus 0.836 and minus 0.548, and here will be 1 and 0, right? R naught matrix. Now once we have the R naught matrix, now use the Gram-Schmidt orthogonalization to get. So this is the R naught matrix we directly get from the direction cosines. The direction cosines we have from the first order reliability analysis. Now once we have this, now apply the Gram-Schmidt orthogonalization using this formula. Now put all these values, you will have this row. We will solve in a MATLAB and we will see step by step. Okay, or you can solve this using calculator too. But this is a matrix operation. You will have the k row, that means R1. These two values you will find it out. We will solve this problem using MATLAB and we will see we are getting this R or not. So R matrix is formed, right? Now, once the R matrix is formed, we need to calculate the D matrix, because we need to formulate the A matrix which contains the D matrix too. Now, what is the D matrix? D is nothing but the second derivative of the performance function in the standard normal space. Second derivative of the performance function in the standard normal space. Now, second derivative, you need to derive the limit state function in twice. So here the partial derivatives are done, and we can see only we have the cross term, remaining term are 0. So we have D matrix.
No,
Yeah.
in forming the R matrix, do you just change the positions and negate uh, the diagonal ones? Because this for R matrix, if you are going to form for R naught matrix, I see negative 0.836 and that. But when it came to the R matrix, I see that the negative 0.548 had removed to the first row, first column, and negated. And then the um, minus 8, negative 8.36 had just been moved to the second row, second column, first row, second column. Is that how it's always done?
Not always that way is done. You need to solve this equation. Here for this 2 by
Oh,
2 matrix, it comes like that. Okay, it's like coincidence. But you just
okay.
need to solve this. Like we have the last row, then above row we will get R1 or R3, we will get the row. Then R1 we will get the row. Simultaneously, here only we have two variables. So 2 by 2 matrix is there. That's why this actually looks like this. Okay, rotational matrix. And recall the rotational matrix formula. If there are two variables, sin theta minus cos theta, sin theta minus cos theta, you can do like this also if you have the theta value. But this is not the case, like I'm flipping out the these things. But I have last row.
All
Now
right.
I can calculate the other row. I
Thank
can
you.
code it, or I can make the do the matrix operation by hand. But it will be larger matrix operation. You did need to do the matrix operation to get the row. Now whatever the value is coming, we will see and check after uh, you know coding or getting the algorithm. Okay,
All right. Thank
because
you.
our matrix should be the orthogonal matrix. Each component should be orthogonal to each other. That's why. Now that's why we are getting these values like this, like minus plus, minus minus, because they are orthogonal to each other. But these values I have calculated or I have found out using this formula. We will see in a minute. Okay. Now D matrix is nothing but the double derivative. Clear? So if we differentiate twice, this term will get 0, get vanish, and we will have the left with the cross term. So this is your D matrix. So we have R matrix, we have D matrix, right? We have R, we have D. Now we can easily formulate the A matrix, right? Because A is nothing but R D R transpose by Euclidean norm of GZ star. But still now we don't have the value of GZ star. What is that Euclidean norm of GZ star, or what is that G matrix here? GZ star. It's nothing but the first derivative of the limit state function in the standard normal space. That means the gradient of the standard normal space. Or we have seen, or we have already know how to calculate it. It's nothing but like gz equals to del gz by del fy dash and del gz by del gz dash. So if you solve these two, you will get the value of 0, 1 and 66. Now once you have, this is the gradient vector of the limit state function in the standard normal space. Now once we have this, we can find out the Euclidean norm. It will be nothing but this square plus this square, right? So we'll have 120. Now Euclidean norm, we have the R matrix, we have the D matrix. So just do the matrix operation, you will find that A is equals to minus this and this. So A matrix we have formulated using the formula. Okay. Now here only two variables are there and they are orthogonal to each other. So the values will be same in flipped form, like positive or negative form. Now once we have the A matrix, what we need to do? We need to drop the last row and last column of the matrix. So here only we have 2 and 2 cross matrix. So we'll left with this. And this will nothing but the kappa 1. Now once we have this kappa 1, just incorporate it within the Breitung model. So PF2, that means PF Sorm or PF Breitung. You can use it. PFB Breitung, you can use it, or PF2 here referred to the second order reliability, second order reliability using Breitung. So it will nothing but phi of minus beta. Now here only we have kappa value 1, so we don't need the multiplication sign from I to n minus 1. So just we have only one value. So 1 minus, this is the beta value, whatever we have getting from the form result, this, into this is the kappa value, and if we solve it, we will get the probability of failure is equals to 1.976 e to the power minus 6. And if you want to calculate the beta, so phi inverse of this probability of failure. So here in this table, here this is already here, phi inverse of this. So here we can see that this is the result we are getting from the form, this is the result we are getting from the Breitung approximation, and these are the probability of failure. We can see the results differ from each other. Now here in our limit state, recall the limit state. What was our limit state? Gx is equals to x1 x2 minus some 1120 1124. So here the degree of nonlinearity is less. That's why we are getting the similar kind of results or nearly similar kind of results. Now if we incorporate higher nonlinearity to the limit state function, or if we have a limit state function which is, you know, or in which the order of nonlinearity is more, then how the results will differ, we will see. Let's say, let's check.
Hello.
Yeah, let's check one problem where the nonlinearity is more. Yeah,
So
yeah, tell me.
so please just go back to the first slide, the slide before this one. Uh-huh.
Yeah,
So if you had a three by three matrix,
yeah,
if you had a three by three matrix, it means that we would have gotten four kappa values.
right. If we have 3 by 3 matrix, let's see, we have 3 by 3 matrix, say 1 2 3 1 2 3 1 2 3. Yeah, then we just left these two values, so we left with these two matrix. Yeah,
Yes.
yeah,
So
2 by
it means that we are going to multiply beta by four kappa values.
yeah, you will eigenanalysis of this matrix. How much eigenvalues you will get? Two, I think, two eigenvalues. So two
Oh,
kappa values.
okay.
Yeah. So actually,
So after, mm-hmm,
after left out this n minus one and n minus one, you need to go for the eigenanalysis of this A, and the eigenvalues of this A matrix will give you the kappa value. So you will have two kappa values.
okay,
So you need
okay,
to incorporate one more line into this. That's all. Okay.
okay, all right.
Here, like you can see, here we have two kappa values, but one kappa value is 0. That's why only one kappa value K22 is used, right, in this matrix. But if we have 4 cross 4 matrix, you need to do the eigenanalysis for this. So we will code it. When we will code it, we will check different kind of problems. Okay. So here, look at the limit state function. Here we have the second order term, x1 square, x2 square, and 18. We have solved it using the form. So after solving it, recall we had these results. Beta is equals to minus beta is equals to 1.9799. These are the two final alpha values. These are the z values, and these are the x values. So we have solved using Reckwitz and Reckwitz-Fissler both algorithm. So these are the final values we are getting from the first order reliability analysis. Now what we need to do? First we need to formulate the R naught matrix. So R naught matrix last row will formed using the direction cosine. So here the value of the direction cosines. So just put the values of the direction cosines, and this first row is calculated using the Gram-Schmidt orthogonalization. Okay. Now here 2 cross 2 matrix, whatever the logic you Bob said, if you go with that, that will give you the same result. But yeah, this is not the correct logic. If you need you go with the orthogonalization equation. Okay. But for this 2 cross 2 matrix, you will get the same results. Okay, no doubt it. Now, once we have the R matrix, we need to formulate the D matrix. What is that D matrix? It contain the second order derivative. Like d squared z by dz1. So you need to differentiate this with respect to z1. You need to differentiate this with respect to, or twice with respect to dz2, you will get this term, and the cos term will follow this. So if we solve it, we will get that only we will have these two terms, there will be no cross term. So we will left with the d matrix as, yeah, actually I lost the connection. Actually, here raining outside, and suddenly the power is tripped. So that's why I lost the connection. Now I hope I am audible, right? Can someone confirm? Yeah. Okay. Wow. Let me go to that picture and picture mode. Then I will start. Yeah. Okay. So once we have D matrix, we can calculate the A matrix. So here the A matrix term. This is the nothing but the Euclidean norm of the gradient vector. That means this is content, like if we formulate the G Z star, what will contain it? Is a vector to cross one. It will contain dgz by dz1 and dgz2 dz by dgz2. The two gradient vector of the two gradient vector of the limit state function in the standard normal space, and Euclidean norm of this is equals to nothing but this square plus this square. Now once we have this, we will have the A matrix. Now just drop these two, we'll left with just one element. So one element, the eigenvalue will be that same. So this refer to the to the kappa value, and once we have the kappa value, we can get the probability of failure using Breitung model. This is the PF Breitung, and we will get the probability of failure this. And once we have the probability of failure value, we can calculate the beta value, just minus of phi inverse of the probability of failure. Now here we can see the results are really differ from each other. Form give that beta value as 1.9799, but solve, that means the Breitung model, whatever we have solved, that means we have incorporated the curvature of the nonlinear function. So here the function, the limit state function was non-linear up to the second order, x square y square. So here we can see that sum is giving the better results, right? That means increase the beta value, that means lower probability of failure, that means this is more reliable, are giving the better results. And we are seeing that if we are increasing the nonlinearities within that limit state function, we are having the better result, because if we have the nonlinearity, the curvature will be there, the A matrix value will be there, and obviously the result will change, right? Now see, let's see, if we go for more nonlinear limit states, like increase it by 5, x1 to the power 5, x2 to the power 5 minus 18. Now let's see how the
See,
result. Yeah.
please, how did you get the square root of 18 in that circle?
Square root of
18, the circle, the
this,
x1, x2 space.
this already given to you na, x1 square plus x2 square minus 18. This is the equation of circle, and 18 square root of 18 is nothing but your radius. It's a basic equation of a circle. It's already
Okay,
given in your
all
problem.
right,
This limit state,
all right.
if forget about the circle and this thing, okay, just look at the limit state. What this imply? This imply the equation of a circle where this
Yes,
18 root 18 is the uh, radius.
the radius.
Yeah,
Okay, all right.
this is a basic equation of that circle.
Yeah, but
Yeah.
I just want to see how it's related to the main question. Yeah,
The main equation,
yeah, it's fine. Yeah,
you got it right.
Yes, I have gotten it.
So now let's solve another problem. Here, this is not the equation of a circle. That's why I didn't put circle here. But we can have this kind of nonlinear function. So here, look, I have increased the order of nonlinearity. Now let's solve it. If we solve it, the problem we have seen that here the final same process you need to formulate. First, you need to calculate the beta, alpha, and final z star values. Then you need to formulate R matrix, then you need to formulate D matrix, then you need to formulate A matrix. This is the basic algorithm. Now once we have the A matrix, drop n minus 1 and n minus 1 element. Remaining A matrix is calculated to find out the kappa values. Once we have the kappa value, we can calculate the probability of failure. Once we get the probability of failure, we can get the beta value. Now look at these values. Like form give you 1.2626, but the Breitung approximation give the higher value of beta. Higher value of beta means lower probability of failure. That means what we have seen, that if we increase the order of nonlinearity, the second order reliability method will give the better result, because only and only if we have the higher order of nonlinearity, we will have the effect of curvature. And once we have the effect of curvature, and if we can incorporate the curvature into our estimation, here through this approximation we have incorporated, so we can have the better or improved probability of failure and beta value. Now what happened if we have a linear function? Then Bob, what happened if we have the linear function, completely linear function?
There,
Then
there'll be coincidence. All the two values will be the same.
two values will be same. Why? Which matrix here will 0 will be 0 for that? The A matrix, because it contains
Mm,
the information about the curvature. Now if we have a linear limit state, there will be no curvature, so A will have no component. Agree with me?
yes.
Let's check here. So it's a simply linear function. Look at this limit state function. Calculate the reliability beta and PF for the limit state function like g x1 x2, 3x1 minus 2x2. Simple limit state linear. Now consider that x1 follows normal distribution with this parameter, and x2 follows log normal distribution with this parameter, and also covariance is there. So if we solve this using form, we will get this value. Beta is equals to 1.9799. On the last class we have solved this problem, and I also upload this problem within your problem set, right? If you run it, you will get this value beta, alpha, and z values. Now let's construct the R matrix. R we will get in this form. The D matrix, the second derivative, because it's a linear function, there will not be any second derivative term. That means there will not be any curvature. So D will eventually 0. And if D is 0, A will be 0. And if A 0, there will be no kappa. That means no information about the principal curvature. That means the probability of failure beta using first order and probability of failure beta using the second order will be same. And here we have seen that actually this is happening. We are having the same values. So I hope the concept of the second order reliability method and the Breitung model, you have the some idea about it. Yeah. So let's see how we can code it, and let's solve these problems one by one, right? Then we will go to the weight model, and we will solve problems for your assignments. Clear? Okay.
Okay.
So let's go to the MATLAB editor, and we will code that algorithm first. Well, is my screen is visible? The MATLAB editor.
Yes.
Great. So recall what was the Breitung algorithm. Let's go to that Breitung algorithm first. We just need to, yeah. So this is the actual algorithm. So of, before getting into that, you know, second order calculations, we need to first run the problem using first order reliability method, right? So let's see. So we need to provide that algorithm, the beta, final design points, and the final direction cosine. So first, what we need to do, we need to first solve the Rakewitz algorithm. So we have seen the Rakewitz algorithm here, the form sum new. If you provide the question number, mu, cx, and index, it will give you the beta value. How it calculate? First, it will check whether your random variables are correlated or not within your limit state function, and based on the value provided, now it will do the equivalent normalization. We have the equinorm function file for it, already we have discussed. Then here it call the limit state function and convert it into z space. Now once we have in z space, it calculate the gradients of this. That means del G by del Z1, del G by del Z2, and we get the alphas. Then iteratively we solve alpha and get the final beta and final alpha values here, right? Now, once we have all these values, now we can call our swarm code. Now we are ready to go for the swarm algorithm. That means Breitung algorithm. Now we will see. Now up to this point, these calculations you need to do using Rakewitz or Rakewitz-Fishler algorithm. Now we are calling this function swarm. Now let's see the algorithm here. So first step, you need to feed all these values, all these final values of betas, alphas, whatever we get from the first order reliability analysis. So this is the function file for the second order reliability method, which I made, that like swarm. If you, what are the input here? The beta, that means the beta you are getting from the first order reliability method. Here first order estimation, I have written it down. Now what is gz? It's the performance function in the standard normal space. We need it because we need to differentiate it twice to get the d matrix. Now dzz is the first order derivative function, like to get the alphas from the first order reliability code. Z for the variable, and zst is the final design points. Now once we have all these values, what it will give? It will give the beta and probability of failure. Now first, like store, first, like we need to provide the final z and final betas and final alphas. So beta, final beta I have provided, and the alpha, what is the alpha? Formula for alpha is nothing but minus of dgz by Euclidean norm of dgz. Already we have calculated it from here. Now we have given the beta value. So alpha and beta already we have feed it here, right? Now what we need to do? We need to so here in the algorithm, we are here up to this part. One second. Yeah. So first part is done. Like we have the final beta, final alpha from the from code, and we have feed it. Now what we need to do? We need to construct the R naught matrix. And what was the property for the R naught matrix? That the last row of this matrix will contain the final direction cosines, and the diagonal term will be 1, remaining 0. So here precisely that thing is done. So R naught, first diagonal of ones, that means one of diagonal is formed. Then the R naught end comma all, that means the last row we are forming. The last row R naught end comma all, the last row is nothing but the direction cosines. Clear? So R equals to R naught here form. R naught, what that R naught content here? Look, 1 in the diagonal form up to n minus 1, and the last row is nothing but the direction cosines. Whatever we have said, we put here, right? Now what we need to do? We need to form the other rows of the matrix. So for the other rows of the matrix, we need to go for the Gram-Smith orthogonalizer. What is the formula? Key, we need to reconstruct or the construct our matrix from n minus 1 to 1 up using this. So Rk is equals to R naught k summation k plus 1 to that Rj R0 k transpose and all this. Just fit this equation here. So here look, n minus 1 to 1. We are going from n minus 1 to 1, right? Now vec plus Rj all this, just I fit that equation here, and R1I and Ri. That means we will get this formula, Ri. That means, let's say we have seventh row, so R6 will be this R6 divided by norm of this. So the total calculation, whatever the formula is given here, look at the formula, you will get, just feed the formula here. That means we are calculating from n minus 1 to 1, n minus 1 to 1, because we have the last row. The last row information will be used, the R0 information will be used, and we make the loop to get the R matrix. So here, if we check R, it will give the R matrix. We will check it is giving the values or not. So it's nothing but we first formulate the R naught, then using the Gram-Schmidt orthogonalization, this is the Gram-Schmidt orthogonalization, R n minus 1 to 1, we are going up, and this is the formula for the Gram-Schmidt orthogonalization already that is given. This is one formula, and here we need to divide it by norm of like Rj and Rj. If you see that the denominator term, we have Rj dot into Rj dot. So that is the norm of Rj dot. I directly written it down. Now here up to this part, we have formulated the R matrix. That means the rotational matrix we have in our hand. Now what we need to do, once we have the R matrix, here we have seen that once we have the R matrix, so we need to find out the A matrix. But before going to the A matrix, we need to calculate the D matrix. And what that D matrix contains? The D matrix actually contains the second derivative of the limit state function in the standard normal space. So second derivative, that means we need to differentiate dz with respect to z1 twice, z2 twice, and we'll have some cross terms. So let's see how we can perform it. So here we can see key 1 to number of variables, we perform d1 is equals to diff first differentiation, then second differentiation of gz with respect to zii and zjj. We have two variables, so two differentiation is done. So the D matrix, the differentiation of the D matrix is done here, right? Now, what was the formula for A matrix? Recall, what was the formula for the A matrix? A matrix will be R D R transpose by Euclidean norm of G. So we have now in our hand R, we have D, and norm of, it's like we have GZ, so we can calculate the norm of GZ. So let's see. So norm of GZ, here I have calculated NM is equals to norm of GZ. There are, or there is a command norm. If you directly write it down, norm of some equation whose value we provide, then MATLAB will calculate the Euclidean norm of this function. Now, once we have this, so A will be nothing but R D R transpose by Euclidean norm of this GZ. So here up to here we get the A matrix. Clear? Now what we need to do? The last row and last column we need to drop off this A matrix. So up to this A will give the full A matrix. That means we will have the complete A matrix. So when we will solve one problem, we will see complete A matrix. Now if we want to drop it, like end comma all last row, here drop it. That means khali kar do ise, make it empty. Now last column also make it empty. So we are left with the n minus 1 and n minus 1 A matrix. Now look, K is nothing but the eigen values of A, right? Now once we have the K values, just put it in the equation of the probability of failure using the Breitung approximation. So this is the probability of failure using the Breitung, PF2 1 plus beta that, and like this formula, this phi of minus beta pi of 1 plus kappa j into beta. So I have separated into two parts, like PF2 first. This is the first order reliability method. That means phi of minus beta, and the second part. Second part, why I am separating out? Because we may have number of k. So we may need to multiply them separately. That's why this part is separated out. We have one variable, we need to multiply it out. But if we have 3, 4, 5 variables, then k1, k2, k3, k4, that's mean the operations are done here, right? Now once we have this, beta, we can find out the probability of failure or total probability of failure as per the kappa value and beta value. Now, once we have done with our calculations, we can directly get here like beta fn2, that will represent the value of the beta we are getting using the uh, Breitung approximation, right? So what we have done here, first we feed the information of beta, we provide the information about the direction cosines. Now from the information of the direction cosine, we provide or we formulate the R naught, whose last row will contain this direction cosines, and other row the diagonal term will contain 1. And then using the Gram-Schmidt orthogonalization, the Gram-Schmidt orthogonalization is also described in the Haldar Mahadevan book. If you want to see it, you can go through it. Now using the Gram-Schmidt orthogonalization, we form the other rows of the matrix. Then once these things are done, we calculate the D matrix. What is the D matrix? D matrix contain the double derivative of the limit state function in the standard normal space. So you need to derive your GZ with respect to twice, like here, like I run a for loop for 1 2 number of random variables. Again, that means the double derivative operation will happen here. Now D, once we have formulate D, we can formulate A. A is nothing but R D R transpose by Euclidean norm of GZ. So first we need to find out the Euclidean norm of GZ. Already we have GZ here. So norm of GZ will give me the value of the norm value. Now once we have formulated A matrix, we need to drop the last row and last column of the A matrix, so that we get the second order approximation. Now once we have that second order approximation, what we need to do, we need to make the eigen operation of that A matrix, and these elements, the eigen values precisely, will give the kappa value. And once we have the k value, just use it like in this model of Breitung approximation and calculate PF of sum. Once we have PF of sum, we will get the beta sum, like inverse of that. Clear how I made this algorithm? So just go through it line by line. You will have it. I will upload it for your reference. So to run this, first we need to have the first order reliability problem. So let's check one problem first, then we will conclude something. Let's say we solve this problem itself. Yeah, this cantilever beam problem, let's solve it. So what is the limit state here? X1 x2 minus we have 1140, right? So let's say first put the limit state function here, x1 x2 minus 1148. So 8 number question we are referring to. Already I am fit that limit state here, so we are referring to the question number 8, right? So in question number 8 we need to fit the initial values. So let's go to the initial values. Now just focus on it. You can see what should be the flow of this algorithm. So first we are calling the form function giving the initial values. So what are the initial value? Like go to the PPT and see what are the initial values. Like we have two random variables. So mu of fy is 38. I have provided here, look, 38 and 54 for x2. Cx, that means the covariance matrix. Covariance matrix you can formulate from the sigma matrix. So covariance here, correlation coefficient is not there. That means directly sigma square will be your covariance matrix, the component of the covariance matrix. So first term 3.8 square and 2.7 square. Look, 3.8 and 2.7. We have two values, right? Now, one more thing. Initial beta we have provided 3, and index, like recall, in this form code the index is used to separate or identify the random variable or the random variable which fall under which group. So here we have log normal variable for fy. So here look, For Fy, we have provided the log normal variable 3 because in our equinorm code, the 3 was the index for the log normal distribution. Now we have two random variable 1, 2, and after providing all this information, I am calling form sum new. First, I am calling the function form sum new. That means first I need to calculate the first order reliability problem. First I need to solve the first order reliability problem and need to get the beta value, alpha value, and z values. So first let's go to that form sum new function file. So here the form sum new function file, what that function file will give, it will give the final results. So first, within that function, here it is calculating the first order reliability problem up to this, right? So up to this we are getting the beta first order reliability probability of failure, z value, alpha values. Now once we have these values, now using that value I am calling the sum function, which just I have discussed, or the sum using the Breitung model. So in sum function file we are providing the beta, that beta I am getting from here itself. Gz already I am providing. DZZ, that means the final GZ values already I am getting from this form code, and ZFN, the final design points. Look, the ZFNs are already there. Now I am calling this. That means from the initial input, first it solved the first order reliability problem, getting the beta, alpha, and the Z value. Now it is calling the second order reliability code. Now what was the second order reliability code? SORM new here. That is the function file for the second order reliability method using Breitung. Weight model we haven't discussed yet. Already weight model is also incorporated here. So here we can see that SORM code, if we in a function file, these are the inputs, Bob. These are the inputs. Okay. On the right hand side of a function file, whatever you have seen, these are the inputs and these are the outputs of the function. The basic structure of a function file. On the right hand side, you will get the output. The left hand side, you need to provide the inputs. And function is like a black box. You provide the input, you provide the structure, it will solve it. Like you don't need to, make one script again and again. That's all. So here, what it is doing, it calculate the first using alpha value. It construct the R naught matrix, then D matrix, and then A matrix, and finally, it calculates the probability of failure, that PF2 value. Okay. Now, once the PF2 value we can also get the value of beta 2. It's nothing but minus of phi inverse of that. So let's say if we run that problem, what we are getting. So case 8, we are running for the cantilever beam. So case 8 already this is. So if I run it, what will happen? We will see. So first, what it will do? First, I will show you one by one. So first, what it actually did, already the simulation has done. So let's see one by one. So first, it's check, is there any, we go for any equivalent normalization or not. So first, it does the equivalent normalization things using the equinorm function file we have discussed. So these are the normal equivalent normal variable with respect to log normal, because one of our variable was log normal. So first it does the equivalent normalization. Actually, first it does the correlation to uncorrelation thing, but here the correlation coefficient is not there. That's why skip that part. Because recall, in the form function file, there I have put one check. First, it will check your CMS matrix is diagonal or not. If diagonal, it will not go for the eigen operation. Otherwise, it will do the eigen operation. Now, once we have the mu and sigma equivalent, we find out the alphas and Zn. So first, these are the ZFN value. That means final design points. Final design points. These are in the Z domain. These are the final design points in the x domain, and these are the final direction cosines using the first order reliability method. Now let's check, is it consistent with our results or not. Like x1 x2 24 and 46, z1 z2 minus 4.2 2.7 and beta 0.059. Look, 24 46, 0.8386 and this, and the beta value, beta using the form is 5 point, wait, yeah, 5.096, this beta fn. Now once we have this alpha values, look step by step, it already have calculated. Now once we have the alpha values, first it constructed the r naught matrix, right? It has constructed the r naught matrix whose last row is nothing but the alpha values. So our code is right. Now it construct the another row using the Gram-Smith orthogonalization, whatever I have, put the algorithm here, this part, right? So okay, now once we have the R matrix, what it does, it look for the D matrix to construct. Now D matrix, the second derivative of the limit state function in the standard normal space, so it, you know perform the second derivative term and give me these two results. Yeah, it also consistent with the values we are getting here. So look, the D matrix, whatever we are getting here, we are similar to this 0.57, 5.878, 5.878, and look this D value 5.78, 5.78. Now this is nothing but the vector of the gradient dzz. That means you don't need to differentiate by your hand. 101 and 66. Look, we are getting this. So D matrix already we have get it here, and this gz star 101 and 66. It has done the first derivative and give me the vector. Now Euclidean norm of gz, just write it down, norm of gz, it will calculate the norm under root of 101 square and 66 point something square, and it will give me the norm of these values. So it is giving the norm of these values 120 point this. Now once we have these all, we can formulate the A matrix. So it calculate the A matrix and give the value of A, right? Now once we have the A matrix, we drop this last one and last two, and we left with the A naught. And using that A naught, it calculate the beta BT. Now beta BT, that means beta using Breitung model, and probability of failure using Breitung model. Gave this to probability of failure. That means line by line, this function file will calculate and give you the appropriate results. Clear? Now Tate already weight model is incorporated within the function file. We will discuss in a minute. So I hope in your mind the algorithm of Breitung or the second order approximation using Breitung model is clear. Yes or no? Now you need
Yes,
to,
we only have to go through. Yeah.
yeah, but you need to practice it lot, then only you can handle this type of problem, right? So you need to practice
Yeah.
it. This basic concept, okay, this is clear, this is the basic flowchart, this is the code, and we can use it. Now let's see, we solve this highly nonlinear problem thing and linear one. Okay, we'll check this too. So that means our code is okay, that function file whatever we have made is okay. If we cross check different kind of problems and it is giving the consistent result, then we can conclude, okay, our function file for this is okay. Let's see, we solve this these two problems. Okay, x1 to the power 5, x2 to the power 5 minus 18, and also this circle problem. So first let's see the circle problem. Let's solve the circle problem. So let's see, I already put the circle problem here. Yeah, Question number 7, x1 square x2 square minus 18, right? So let's see in question number which question I have seen, question number 8 7, question number 7. So already I have put the values here, that means the initial inputs. So question number 7, so you just change the question number here 7, and we check that whether we have put all these information correct or not. Yeah, we have two random variable. We have the C covariance is 5 5 and mu 10 10. We have two uh, normal random variable, that means we don't need to go for equivalent normalization. We have only two random variables. Now run it. Let's check whether it is giving the better results or not. Yeah, so let's check. This is the beta using the first order beta fn, that means the first order beta. This is the pf, that means the first order pf. Now beta bt, look, the beta value have increased, right? Whatever we have the values here 2.2222, right? So we are seeing that yeah, our function file is working well, and we can see that if we increase the nonlinearity, it is giving the better result beta value. And if you check the pf value, you will check the pf value also. Pf of Breitung 0.0131. Now if we want to increase the nonlinearities further, like that square to 5 term, question number 9, if we run the question number 9, so the GSC file, you recall the in GSC file used to put the we used to put the limit state functions. So question number say 9, if we run it, and we will see what will happen. There's a highly nonlinear function, it is running. Let's check how much it will take time. But still, these function files, if you use them, these are quite lighter, and that will not take much time for your calculations. Okay. Yeah. Okay. So beta, look, in first order term, if we solve it using first order reliability method, we have beta is equals to 1.2626. Probability of failure is equals to 1.01. Now, if we go for the second order, we get that the beta using Breitung approximation, we are getting 1.5302, right? And simultaneously the PF will change. Obviously, beta value, if the beta value will increase, the probability of failure will decrease. And we can see the probability of failure is decreased. That means it's okay. And simultaneously, we are having the same results here. Here, look at this. Okay, that means if the nonlinearity will increase, the SORM will give you the better results. Now let's check for a linear problem, is it okay or not? Then we will conclude the okay, our function file whatever we have made is okay. So let's see, we will check the linear problem with the correlation coefficient. This problem, right? Calculate the reliability index beta and pf for the limit state function 3x1 minus 2x2, where x1 and x1 follows normal, x2 follows log normal, and there are correlation coefficient. So if you want to check it, just first you need to put the limit state function. So just put the limit state function. Question number 1, 3x1 minus 2x2. I put it here, 3x1 minus 2x2 only. Now you need to incorporate the initial values or the values of the random variables. So here we have two random variables. First random variable, the values are already given here. You can see on your screen. Like first random variable, the mean is 16.5. So here look, 16.5 is given. And the second variable, the mean is 18.5. But the second variable is log normal. That's why the indexing is changed here. That means you need to you need to normalize it, or you need to get the equivalent normal parameter for this log normal distribution. Then only you can proceed for the rest of the calculations. Okay. Now all the values I have given, now just run it and check whether all the values are same or not. What is the flow? First it will check the correlations, then uncorrelate it, then it will check the it will check the equivalent, uh, or if we need to make the equivalent normalization or not, then it will call the gx, convert it into gz, then make the first differentiation, get the alpha values, start iterating, get the final values, get the final alpha values. Now once we get the final alpha and beta values, go to the sum code using the final alpha, construct the R naught matrix. Once the R naught matrix is done, construct the R matrix using the Gram-Schmidt orthogonalization from n minus 1 to 1 row. Then calculate the probability of failure using Breitung model. Clear? That's all. Now see, let's see our results. Okay, it's I've already run, and look, all the values are same. Yes or no? From Breitung, probability of failure 0.05, first order 0.05, first order beta 1.15, second order beta 1.15, and if we go above 1.59, same. That means our code, whatever we have made, is working well, and it can handle all kind of problems like this problem: correlated non-normal linear. We have correlated non-normal non-linear, it also handle it. Okay, now you can see that the first order approximation and the second order approximation will differ if the nonlinearity will increase, because in the linearized approximation we are not having the actual probability of failure domain. That's why this phenomena is happening. Okay, now let's see. We have another model called Tate model. Just we go through that model very quickly, and then we will solve our assignment related problems. So here in the Breitung approximation, we have some limitations, like this model will not valid if beta kappa j is less than 1. That means for the negative curvatures it will not work. And as it we at is use asymptotic approximation, like we haven't discussed the asymptotic integral part. It's like you can go through that paper or the videos of Professor Arunasi Chakraborty, you will get it. Now it will uh, give, like, if I have the beta value like 2, 2.5 or more than 1, it will give the accurate value. But for the lower value of the beta, it will not give you the appropriate result. But for the engineering application, we don't need to think about the lower beta, because we all have the beta like around 2.5 to 3.5 or 5.5. So the model will work. Now, one more model we have that called the weight model. Now Tvedt actually what he did, so here in this publication you will find out all the derivation, all these things. I am not going into the derivation part, I just go to the model. So in the weight model he used that three term to approximate the limit state function, or the second order approximation function, and give the three term that probability of failure. If you want to calculate this model, it will contain the three term a1, a2, a3. Now a1 is nothing but the Breitung approximation. Here you can see A1 is nothing but the Breitung approximation term, and over Breitung approximation he made some two approximation and gave these formulas. Uh, Now what do you need to do if we want to calculate the probability of failure? You need to add these two terms using the Breitung approximation formula. Now once we have the PT weight, we can get the beta nothing but minus of phi inverse of beta, right? So what should be the algorithm for this code? First, we need to calculate up to the Breitung approximation, because from this approximation we will get the A1 term. Now we need to make two more terms here for the additional curvature information. So A1 and A2. So your PF will be nothing but Breitung approximation plus some approximation over the curvature part. Okay, so let's say we just need to incorporate these three things. So let's say go to the code and incorporate this. Already weight model is incorporated here. So in short, like, once we have calculated these three things, now here look, the first term a1, so I have put it here in1. This is the second term, this is the third term. So probability of failure 3, that means it indicate the probability of failure using weight model. Now in1, in2, in3. This is the probability of failure. Once we have the probability of failure, beta fn3 is nothing but minus phi inverse of pf3. So here this function file that SORM new will give you two results. What? One, the beta of Breitung, corresponding probability of failure of Breitung, that means beta fn2, that is the beta using the Breitung approximation, beta fn3, that means the beta using the weight approximation, and two probability of failure. That means here if you see the results, you can see it is calculating the beta bt, that means beta Breitung, beta ttt, that means that weight model or the three term approximation, and two probabilities. That means if you run the whole code, first it will calculate the first order reliability method using Rackwitz or Rackwitz-Fishler algorithm, whatever switch you want to on. Now it will calculate the Breitung approximation, and lastly it will calculate the Tvedt approximation, and it will give you that three probability of failure values. Like for one example, like here we can see we have examples. Like for the highly nonlinear case, we will check. Okay, rest of the examples I have added here, you can go through it, you can run the code, you can get all these values one by one. Let's see for the highly nonlinear case, what should be the values if we incorporate the weight model within this. So from the ppt you can see that further, look, Breitung gives 1.53, but weight gives you 1.57, little higher value. That means little less probability of failure. That means only on if you have the highly nonlinear function, weight will give you more accurate result on beyond your Breitung model. Like if we run this problem of this and check whether sorry, whether the values written in this they are in the ppt is okay or not. So what does the limit state? Question number 9 gives you the limit state. So just run the question number 9. I'll check. So it will calculate all the things, you run it, all the values you will get it one by one, one by one, one by one. So let's see what value it will give us. This book you can refer for this second order reliability problem, Haldar and Mahadevan. Is it visible? Yeah, it has give the results. Like look, first it will print the beta value using first order beta fn, first order reliability index 1.2626, probability of failure this. Now using Breitung approximation this, using Tvedt approximation this. Look, the Tvedt has increased, like A2 and A3 term will only appear when the large nonlinearity will be there, and the probability of failure will subsequently change. Now you can run another problems and you can check whether your results will vary or not. Clear? Okay. Now let's quickly solve some of the problems, then we will discuss quickly, and you will solve this problem with me. So say for example, okay, start with a statement, then we will go to here. Yeah. So tell me which are the correct statement. SORM will give better result of failure of probability than form when the limit state equation is nonlinear. Tell me, Bob, is it correct or not? Second order reliability method will give better results of failure of probability than form when the limit state equation is nonlinear. Is the statement is correct?
Yes.
Yes. We have seen it and we have checked it also. So it is yes. Now in SORM, the up to the second order term in Taylor series expansion is considered, which is ignored in form. Is it correct? Yes or no? Second order. Obviously, second order term we move up to the second order term, which is actually ignored in first order method. So is it correct or is it wrong? Correct. Right, Bob?
Yeah, correct.
Yeah.
Yes, correct.
Yeah. Now, the curvature of any equation is related to the second order derivative with respect to the basic variables. Is it true? Yes. Any nonlinear equation, the curvature is related to the second order derivative. That D matrix and A matrix that contain
Yeah,
the second order term and is the basic mathematics, like the curvature of any nonlinear equation is related to the second order derivative with respect to the basic variables. So is it correct or not? Correct. Yes. Any doubt? No. Now the curvature of the limit state around the minimum distance point determines the accuracy of the failure of probability. Is the statement is correct? If we have nonlinear function, obviously the curvature around the MPP will determine the accuracy of the failure of probability. That's why we go for
yeah,
the SORM. Otherwise, we stick to the form. So it is also.
correct.
So all of these are correct. Yes or no? Do you have any dilemma? Yeah, no, this statement should be wrong. We have seen the second order reliability method, how it's improved the results of the first order reliability method over the form, right? Okay, so clear. Now let's move to our questions. Let's see. Yeah. So here the for a given limit state function, beta is given, that is obtained from the first order reliability analysis, and the principal curvature kappa 1 is also given. Then find the failure probability as per Breitung model. Very simple question. What is the failure probability using Breitung model? PF2 already you have seen, phi of, that means standard normal variate of, minus beta multiplied by, here only one kappa is there, so this multiplication sign we don't need, so just write it down, 1 plus beta
You,
k1 to the power minus half, and check whether we are getting this value or not. Check it. So here already we have all values. Phi of minus beta divided by under root of 1 plus beta k1. So phi of minus beta, you can calculate it using standard normal table, or you can opt for your calculator. You know how to calculate that phi of minus something or phi of standard normal variate. Go to stat mode, go find out the p value. I already have told you, right? Or you can directly go for the standard normal table to find out this value. So this value is nothing but 0.084 and divided by this is coming as the answer, right, Bob?
yes, yes, it's okay.
Exactly. Now move to the second question. What this question says, for a given limit state function, the second order reliability index as per Breitung model. So beta Breitung. Breitung is a Breitung. As per the Breitung model, we have the beta is equals to 2. The value of A1 and A2 is 0. As per the weight model, the failure probability is k multiplied by 10 to the power minus 2. Calculate the k value. It's a very simple question. What is the probability of failure using the weight model? PF3 is equals to A1 plus A2
A2
plus A3.
plus A3.
Yeah, A1 we have already, like from the Breitung model, we have beta is equals to 2. So we can calculate the A1 value. So A1 comes out as 2.2 into 10 to the power minus 2. Clear? Now A2 and
Yes.
A, yeah, Bob.
I say yes, go ahead.
Yeah. Already we have kappa value and beta value. Already we have, then we can easily calculate it. Now, once we have that A1, A2 and A3 as 0. So this total A1, A2, A3 is equals to this. Now, what that says that the probability of failure is given as k into 10 to the power minus 2. Now solve the equation and get the value of k. That's all. Clear?
Yes.
Great. Now let's move to the second question. Here, for a given limit state function, beta is given as 2.85. As per the form, the principal curvature is also given. Breitung model. You just need to put all these values in this equation, right? So PF2 is equals to 5 of minus beta 1 plus this kappa value. And if you solve this, you will get the value as 1.088 into 10 to the power minus 3. Are you getting it? Not? You can check it. Are you getting the values like this? You just need to
Yes.
solve. Yeah. Now move to the last say yeah, this question. Let's see what this question says. A limit state is given as gx equals to x1 x2 minus 1600. Now x1 follows normal distribution with mean 70 and standard deviation 5, and x2 follows also normal distribution with mean 30 and standard deviation 4. Find out the D22 term of the D matrix. So D matrix contain the second derivative terms, right, of the limit state function in the standard normal space. So z by dz1 dz2 del gz by del z1 del z2 and del gz by del z2 square. So you have the limit state in the actual domain. First you need to convert it into standard normal domain. So what was the formula for conversion? X1 is equals to, think, say Z1.
That, that yes.
Yeah, Z1 is equals to X1 minus mu X1
You
by
was
sigma X1. So this is the formula. So X1 is equals to, like here directly I am getting X1 is equals to Z1 into sigma X1. This part 5 into Z1, and this is mu value. Look, mu of X1 is given as 70. Okay, and for the second variable the mu is given as 30. So mu plus sigma into z2. So x1 and x2 we already have. Now substitute this x1 x2 into gx, so we will have gz. Yeah, this one x1, this one x2, and this is 1600. So simplify it, just multiply it and do the multiplication, you will get gz equals to this. Now what you need to do, you need to differentiate with twice with respect to z1. If you integrate differentiate twice with respect to z1, what you will get? 0. So first term will be 0. Obviously if you differentiate twice with respect to z2, you will get also 0. Only you have the cross terms, so just make the derivations and check what are you getting. So del square gz by del z1 del z2, it's come out at 20. You can check it also. So what will be the d22 term? This is 20, this is 20, this is the whole D matrix. So d22 term will be sorry, d12 term, d12 term,
1 2
12 term will be 20. What will be the d22 term? 0. 2 and 12.
0. Yeah. 0.
Yeah. Now let's move to, yeah, here we have another question. Let's solve it also. So for a given limit state function, the rotational matrix R is given, and the matrix of the second derivative matrix is also given. That means your R and D matrix are given. The length of the gradient vector, that means Euclidean norm of the gradient vector GZ star, is also given 42.426. The length, that means the gradient already given. You don't need to calculate it. Now what you need to calculate, what will be the A11 term of the A matrix. That means you need to calculate or formulate the A matrix first. So A matrix, how we can calculate it? R D R transpose divided by Euclidean norm of Z star. So this value is already provided as 42.426. R matrix already provided here, D matrix provided here. Just do the matrix operation, you will have that A is equals to this. Okay. Now once we have the A matrix, A11 will be this, A12 will be this, A22 will be this, and all these things. Clear? So A11 will be 1.1785, nearly equals to 1.18. Clear? Okay. Okay. Now I think we have one more question left. For a given limit state function a1, a2, and a3 are given, what will be the probability of failure using Tvedt model? You can solve it. Yeah, we don't need to discuss it. Like so,
Yeah,
basically, then let's conclude today's session. Like what we have learned today. So I hope you can now able to solve your assignments and submit it. Now
yeah,
our goal is not to submit that assignment. Our goal is to understand that second order reliability method, how we can incorporate it, and when actually we need that second order reliability method. When the question has been solved, like when we have highly nonlinear limit state function. So when we have that highly nonlinear limit state function, we cannot go for the first order linearization because the truncation error will give us the erroneous results. Now in the second order reliability method, if we solve using Breitung approximation, what we have seen that Breitung have proposed some closed form solution using the theory, or we can say concept of asymptotic integral. He proposed and closed form solution. Here we can see that if we have this model, we can easily calculate the value of probability of failure using this equation, and once we have the probability of failure, we can easily get the corresponding beta value from here, right? Now to do this, we need to calculate the kappa values. This actually contain or tells us about the curvature value, because we know that any nonlinear equation, the curvature or the second derivative of this limit state with respect to the basic variables will tell us about the curvature. In the very first beginning, we have seen it. Like I already have discussed it. You actually joined late, that's why you missed that. Like here, the curvature of any equation, the last point you can see, it's the basic mathematics. Like curvature of any equation is related to the second order derivative term. That means if we want to consider the nonlinearity or incorporate the nonlinearity within our estimation, we need to go up to the second order term. That means we need to truncate the series up to the second order term. Now we can truncate the series into, like we can consider up to different kind of terms, but computationally this will be more mm, uh, more heavy, or we cannot, like if we want to run it for 10,000 times, we cannot run it, or it will consume a hell lot of time. So it will slow us down. So we have like two models using with, or the Breitung. Out of them, Breitung actually the popular model. Like we see that if we have these two or three information, like what are the values of the final alpha, what are the value of beta. That means what you have seen about the Breitung approximation, it does some correction of the first order reliability estimation using the information of the principal curvature, or using the curvature to incorporate the nonlinearity into our estimation, or into the problem of our estimation. Okay, so that's actually today's content. So we have already solved it, and we have also seen that when we have increased the nonlinearity, the results from the form is actually differ from the result from the sum. Obviously that if we have the higher nonlinear limit state function, the zone of the failure probability will be different, and if we have the different zone of probability of failure, then obviously we'll have different values. Now the question is here, the question is like, for example, if we consider this problem, like beta form give me 1.26 value, but swarm give me 1.53 value. So if you go with the form value, that means you are actually underestimating your design. Yes or no, Bob? Because the failure
yes,
probability is
it's true.
higher. So we, for the safer side, we need to go up to the actual order of this nonlinearity. That's why, like generally we use the reduced order model and all these things, but actually in the reduced order model, these are the computationally efficient, but the trade-off between this is you don't have the exact result. So you need to go up to these values, like the simulation based technique. We have Monte Carlo simulation and all these things. We will see during the next 2 or 3 classes, that how we can calculate the probability of failure without knowing the much information about that analytical model. We can directly calculate it, but computationally this cost more, like in FEM model. So if you have any background about FEM, then you can see that the FEM model are robust, but they are computationally more heavy. That means we have a whole lot of degree of freedom. We need to compute for all degree of freedom again and again, again and again, and all these things. Then we will get, but we will get the actual and proper results. Okay, let's talk about your assignments. How you are getting marks about your assignments? Any doubt and questions about assignments? Bob, you are sitting for the exam, right?
Yes.
Yeah. So I think that 25% marks will directly be from assignments, and rest from the final exam. Okay, I will conduct one class, particularly 1 hour, like when we reach the 12 week. So 12 week, I will discuss about the final question. What kind of question will come? How you need to prepare for the questions? And I can assure you, if you go through that assignments, if you make a note about the assignments, then 70 and say 75% question will come from your assignment. Still, rest for the rest kind of the questions we will discuss dedicatedly. We will put on class, 1 hour class for this, so that you will not feel any kind of trouble during the exam. Like already you have felt that this course actually is not for the like undergrad or postgrad students. It's like research level, or if you want to learn something advanced or incorporate something advanced in your career, or in your in your progress. So then you should pursue this course. But this course is very
Sure.
important. Yeah, but very
It's a
important,
heavy
like,
cost.
yeah, but this is very important. Here you already have learned that how we can incorporate the nonlinearity into our design process, and we can make them reliable without knowing the
Yes.
factor of safety. That is the main takeaway of this course. Like, maybe one variable may be random. You can put up a question like, we are giving that factor of safety this 3, but maybe this kind of randomness may come. How we can model it? And if you model it, and if you want that probability of failure, this, what should be your design point? Give me the design point. Now you have a method, you have some logic to solve this, incorporate the randomness, and get the desired probability of failure as well as the desired reliability. Once you have the probability of failure, you can say that the reliability will be 1 minus that, and you will have the reliability corresponding, right? Okay, so
Yes.
don't
Yes.
worry
Yes.
about the final exam. We will discuss one dedicated class for this question entirely. That day we will discuss one by one from every module. We will that uh, to discuss and solve the question, whatever may this kind of question may come in your final exam, right? Okay, so you have any
Good.
questions, or we
No,
can,
no.
yeah. So okay,
Yeah,
then
it's excellent. Yeah.
yeah, so let's meet on the last next class on next Sunday. Okay, for now, thank you.
Thank you very much.
Thank you. Okay, so I'm ending the meeting. Okay.